Consider the following problem. We want to drive by car from an origin to a destination. The trip is quite long and we need to fuel up our vehicle on our way. The car has a maximum fuel capacity of k liters. At the start, we have B0 liters of fuel on board. We checked our route and found that there are a couple of gas stations along our way. Quite naturally, the gas stations partition our trip into n+1 segments. Traveling segment I requires VI liters of fuel. It makes sense to assume VI is less than or equal to K and V0 is less than or equal to V0, because otherwise we wouldn't be able to reach the next gas station. At a gas station we can buy fuel if we like to. Let xi be the amount of fuel that we buy at gas station I. This is a decision variable, and the value 0 means that we do not make a stop at that gas station. The price per liter is Pi at gas station I. How can we reach our destination in the cheapest possible way? Can you formulate a model for this problem? Give it a try and pause the video now. One way to approach this modeling problem is to consider a timeline along which a fixed number of events occur. At some point of time, we start our trip with B0 liters of fuel on board. Then there is a phase of driving until we reach a gas station. During this phase, we consume fuel. After the arrival, there might be a phase of fueling where we fill up the tank of our vehicle. As soon as we leave a gas station, the pattern repeats. After the event of departure, we have a driving phase, and a fueling phase. And a driving phase, and a fueling phase. And so on. In this example, the objective is quite forward to formulate. We want to minimize the amount of money we have to pay for fuel. When it comes to the constraints, it helps to figure out what a so-called state of the system could be. In our case, the state of the system could be the fuel on board upon departure from a certain location. At the start, the initial state is described by B0. When we leave a gas station, the state, that is, the fuel on board, can be described by B1, B2, and so on. Which are decision variables. The state must fulfill Vi is less than or equal to the capacity and going from one event to the other, the state is modified by the actions that take place in between. Formally, we have the new state equals the old state minus fuel consumption plus The domains of the decision variables complete the model. This example shows a typical approach for modeling whenever we can decompose the problem into a sequence of subsequent events along a timeline. The events can often be linked when we succeed to find what we called the state of the system, and a rule for changing the state when we move from one event to the other in chronological order.